Okay, good morning. This is Engineering Statistics and Linear Algebra. We are in the module 2 now, and we will discuss today the multiple random variables. And the specific topic which we will be discussing is the bivariate CDF and PDF. But in the syllabus, what it is written is two variable CDF and PDF. Whether it is bivariate or two variate, it is just the same, right? Then we can extend it to the multiple variate also, right? Further to this, till now in the first module, we have been studying about the single random variable. Many of the things will be just extension of the, the single random variable or SRV to the MRV, single random variable to the two variable, whatever CDF and the PDF which we have. Okay, single CDF PDF, the extension will go to the bivariate or two variable CDF and PDF. Okay, so first we discussed about the CDF for a single random variable as fxx is equal to probability of x less than or equal to x. Fxx is equal to probability of x less than x. This can, we can consider an example of a throwing of a dice over here. Okay, the CDF for the what you call throwing of a dice when x is the value 2 will give us the value p of x less than or equal to 2. P of x less than or equal to 2 will be equal to P of x equal to 1, P of x equal to 2. That will give us the value 1 by 6 plus 1 by 6. For a throwing of a dice, each of the value 1, 2, 3, 4, 5, 6 probability will have 1 by 6. So P of f of x2 will be equal to P of x less than or equal to x. That will be P of x equal to 1 and P of x equal to 2. And that value will be 1 by 6 plus 1 by 6. That will be equal to 2 by 6 or 1 by 3. Okay, 33% will be the probability of having the cumulative distribution function which corresponds to, the value x equal to 2. Similarly, if we talk x equal to 3, then this value will be equal to P of x less than or equal to 3. And that will be P of x equal to 1, P of x equal to 2, P of x equal to 3, all the three components added together. That is 1 by 6 plus 1 by 6 plus 1 by 6. That will be equal to 3 by 6. That will be 1 by 2, half. Okay. Similarly, if I take x equal to 4, it will be 4 by 6. X equal to 5, it will be 5 by 6. X equal to 6, it will be 6 by 6. So that means as the value of x is increasing, the value of xxx is f of xx will be increasing because that corresponds to the probability. So cumulative distribution function always increases. It can never decrease. We say monotonically increasing in a general case. Monotonically increasing means it never decreases. It can either increase or it can remain same, but it can never decrease. That is for CDF. Do not confuse between CDF and PDF. Okay, PDF can increase and decrease, whereas CDF is always the probability. Okay, and that probability should keep on increasing or might be remain constant, but it cannot decrease, and that we call it as monotonically increasing. So extending this for two random variables, we can say that we have here f of x, y, x comma y, and now we will have both x less than or equal to x and y less than or equal to y, and that will give us the intersection and the intersection between these two. So both x less than or equal to x and y less than or equal to y should occur in the probability distribution function. Now this can be considered for throwing two different dices. Okay, two different dices together. So if we want in the first dice the value say x equal to 3 and the second dice the value equal to 2, then that will give us 3 here and 2 here. So naturally 3 here and 2 here will give us the corresponding values over there, and we can again take the value, so to say, that will give us the value will become 3 into 2 divided by 6 multiplied by 6, okay, divided by 6 square. 3 into 2 multiplied by 6 square, that might give us 6 by 36. That will be 1 by 6 if I say that the x value is 3 and y value is 2 in case of throwing of a dice. Okay, so like that you can keep on taking the pattern for different examples. Now extending it to a multivariate, that means if in place of xy, say if you have x1, x2, x3, xn, different random variables, then this will become the total probability corresponding to that, and the CDF corresponding to that will be equal to the intersection of each of the cases. That is x1 less than x1, intersection x2 less than x2, intersection ... xn less than or equal to xn. Okay, so that can be extended in that way. So going in the same way, we see that whenever we talk about the two variable things, then what is the correlation, what is the relationship between x and y rather becomes very important whenever we take two random variables. How the x, y are related at all. How x, y are related at all. For example, if you say that the event x corresponds to throwing of a dice and event y corresponds to throwing of a coin, then we know very well they are not related at all. Okay, they are not related at all. So when they are not related, then the probability will become 0 corresponding to that. But if we say we are throwing a dice as well as throwing a we are throwing two different dices, then they are definitely related with each other. So if the events are related with each other, right, there is a correlation between them, there is some affinity between those two, then we will have some sort of relationship between them. And corresponding to that, if the two random variables are having a correlation means a relationship between each other. More the correlation, more will be the value of the CDF. Lesser the correlation, lesser will be the value of the CDF of the two random variables. So correlation just means what is the relationship between the two different events, two different variables, x and y, x1, y and z, or x1, y1, z1, or x1, x2, x3, x4, x5, if you take a multiple random variables. Okay, so you can plot for multiple random variables, but we can definitely plot the relationship between the two different random variables. So if the points plotted will turn out to be like this, you can see that the slope is positive. Here, if the points relationship between x and y is this dotted gives by this dotted points, then the slope of this is approximate slope, which might be drawn between these points. Okay, will give you the slope which is the negative slope. This is a positive slope, this is a negative slope. There is no correlation here. Okay, there is no correlation here. So this is positive, this is negative, this is no correlation. So correlation positive, negative, 0, and that will literally give us the positive correlation coefficient, negative correlation coefficient, and 0 correlation coefficient between x and y, two different variables x and y, and that is the plot with which we will get that thing. Now let us consider how the bivariate cumulative distribution function can be derived or considered for, from the single random variable. So if we have f of x, y, x comma y, where we are considering the CDF of two different random variables x and y, then how it can be visualized, how it can be considered. Okay, so if we consider, we can consider this figure. So say we have the probability for something which is less than xy. Okay, less than xy. So this will be the area corresponding to that. Now if this point we move a little further, that is x plus del x and y plus del y, then the area which is there here, that will give us the difference. That will give us the difference. And that difference will be the what you call, we can call it as dp. Okay, difference in probability. Difference in probability from this figure to this figure, this figure to this figure. So that means this is nothing but this. This is nothing but this, in an expanded form. Whatever is there within this is there here. Okay, and the rest of the portion is your dp. Okay, whatever is dotted here is the dp which we have. So we can consider the CDF evaluated once at x comma y, and again evaluated at x plus dx comma y plus dy. Then the difference between the two bivariate CDF is the probability, which is dp, which can be represented like this. And this is basically you can represent it by means of the Taylor expansion, and that Taylor expansion is written over here. That is f of x is equal to f of a plus f dash a x minus a plus f double dash a by 2 factorial x minus a squared plus f triple dash a by 3 factorial x minus a cube plus etc. Now we will take an approximation for this. That means we will neglect the terms which are from second order, only the first order and the 0th order. This is 0th order and this is the first order. Only those two if we consider, then we will get only these two terms. We'll get only these two terms. That means the FA value, or rather f of xy, if we take this, if we expand this over here, right? So we will get here this, the value of f of xy will get cancelled, and we are left with dou by dou x of f of dou by dou x will be just the f dash component with respect to x, and dou by dou y will correspond to the differential with respect to, that is f dash with respect to y. Okay, with respect to y. So this is two-dimensional, whereas you might have written here one-dimensional. That's all. So in the two-dimensional, we will have this quantity is equal to this plus these two, considering only the first ordered value. Second order, third order, and all are neglected. So the differential dx, dy are positive. Whatever we have here are positive by the assumption in the figure 3.3, because we have written here, this is a positive area. Therefore, those two quantities should be positive. These two should be positive. Therefore, the bivariate CDF must be non-decreasing, monotonically increasing, non-decreasing or monotonically increasing in both the x and y directions. Again, similar to the one-dimensional, CDF, the CDF is non-decreasing or monotonically increasing. This is very important concept. Please do not forget. Okay, the concept is the CDF should always be non-decreasing. CDF should always be monotonically increasing, and that means either it can increase or it can remain same, but it can never decrease. So we can consider certain special cases over here. That means x less than of minus infinity, and again similarly y less than or equal to minus infinity. If we have, then that will give us the value which is an impossible event. F of xy, if you take for single variable, then definitely x less than or equal to minus infinity is an impossible event. For example, if you have a throwing of a dice, right? For a value, the possibilities in the throwing of a dice are 1, 2, 3, 4, 5, 6 over there. Okay, 1, 2, 3, 4, 5, 6 over there. So if you take a value which is something other than this, if you take a value which is something other than less than 1, that means 0, minus 1, minus 2, minus 3, naturally the probability of an occurrence of a minus 1 or a 0 or a minus 2 or a minus 3 will be equal to 0 for a throwing of a dice. So therefore, in the same way, if you consider it, okay, the extension over here for any negative values of a in a event are not possible at all. So if you take that, extend it, f of xy minus infinity comma y, x is less than minus infinity. Here, this is nothing but x is less than minus infinity, and x is less than minus infinity will definitely give you the value of phi here. So 5 intersection with something will definitely give you phi. Something null intersection with another value will be null only, and therefore the probability of that will be a null, and that will give us the value which is 0. Okay, probability of a null will be equal to 0. Similarly, if you make y less than or equal to minus infinity, we will have this quantity, and again going on the same lines, this will be p of x less than or equal to x intersection phi, corresponding to p of y, y less than or equal to minus infinity. Corresponding to this minus infinity gives us y less than or equal to minus infinity. Here, minus infinity corresponds to x less than or equal to minus infinity, and for that we have an impossible event phi. Similarly, this minus infinity will correspond to y less than or equal to minus infinity, and again that will correspond to impossible event phi, and therefore that will be x less than or equal to small x intersection phi, and that will give us the value 0. P of x less than or equal to uh, x intersection phi, and that will give us 0. If you take both x and y, definitely, minus infinity and minus infinity, that will be P of phi intersection phi, that will definitely be 0. Okay, that will definitely be 0. Now, if we can take another special case where x less than infinity, please differentiate between this. This is x less than minus infinity, which is an impossible event. This is x less than or equal to plus infinity. Minus infinity and plus infinity are two different things. Minus infinity, less than minus infinity is not at all possible. Less than infinity is totally possible, or definite event, certain event. We can call it as a definite event or a certain event, and a certain event will be given by a event s, and the probability corresponding to a certain event will be equal to 1, and this will be a certain event full, and certain event intersection y less than y will be y less than y itself. Okay, s intersection y less than y will give us the value y less than y, because this is definite event. Okay, definite event means in sets it will correspond to the whole of the space, and whole of the space intersection with a small space will give us the small space itself. Okay, this is set terminology. We can see that S corresponds to whole of the space, Y corresponds to a space where y less than equal to y is corresponding to space where y dimension is less than y, and therefore that will give us p of y less than or equal to y, and that will be f y. Going on the same lines, if we consider here, we are considering x as infinity. If we consider y as infinity, this will give us fxx. Okay. Now, these two, that is, these two special cases over here are known as marginal CDF. Marginal CDF. If we make both of them, infinity, x and y infinity, then naturally that will correspond to a definite event intersection with a definite event. That will be what you call a total probability, and that total probability is 1 itself. Okay, total probability, we know it is 1. Probability cannot go above 1. Probability should always be between 0 and 1. Okay, so impossible event 0 probability, definite event probability 1. Only one side, if we have definite okay, or certain event, then only the other component will come out. That means x is infinity, only the other component will come out. X is infinity, x will go. Similarly, if y is infinity, y will vanish from here, and we will have fxx. If both are infinity, then the probability will be equal to 1. Okay, this is a very important thing, and that's generally known as the marginal CDF. Fxx and Fiy are called the marginal CDF in the case we have one of them, going till plus infinity. So then let us come to the bivariate probability density function. If you have any doubts till now, you can ask. I'll just. So we'll go for the next topic, which just corresponds to the bivariate PDF from the CDF. So till now we considered the bivariate, CDF, and we considered that bivariate CDF is monotonically increasing. That just means non-decreasing. Okay, non-decreasing. If one of the quantities is less than minus infinity, then the bivariate CDF will be equal to 0. If the one of the quantity is less than infinity, only the other variable will come out, and that is known as marginal CDF. Okay, if one of the quantity is less than minus infinity, then the CDF will be equal to 0. If one of the quantities is less than infinity, and that is a certain event, then the other variable, other quantity will take over. And when the other quantity takes over, that is known as marginal PDF. If both of them are less than infinity, then the CDF will be 1. If both of them is less than minus infinity, the CDF will be equal to 0. However, always remember that whether it is the bivariate or the single variate CDF, it will be non-decreasing. It will be non-decreasing. Okay, it will always be increasing, right? It will always be increasing or equal to same. It will be always increasing or equal to same. Okay, so it will never be non-decreasing. So now bivariate PDF is what we have. So similar to the CDF will be, if I have a what you call PDF will be what you call the PDF will be the differential of the CDF. We know it very well. So in the same way, for a two variable PDF also, that will be the differential with respect to both the variables, the CDF value. If you differentiate the rather more particularly the partial differentiation with both the variables x and y, okay, the partial differentiation with both the variables x and y need to be considered for the CDF to get the PDF. Okay, so that just gives us that small f x y x comma y is nothing but the PDF, the bivariate PDF, and that will be equal to dou square by dou x dou y. That is the differential of the CDF over here, So that will be definitely, we need to go from continuous function xy. There exists only a finite number of places where this dou by dou x of xy and dou by dou y f of xy do not exist. So this is the assumption we'll always make. That is dou by dou x of f of xy and dou by dou y of f of xy do not exist only at a certain number of places. All places it is going to, okay, be present. Okay, all places it is going to be present. Okay. So at certain points it might not occur, but all other places it will always exist. Okay, so from the 3.9 which we have written over here, we can always write that because it is nothing but the probability over there, the value of f of xy x comma y is greater than 0. Okay, always the PDF is greater than 0. So it follows from 3.9, and from the fact that bivariate CDF is non-decreasing in both x and y direction, that a bivariate PDF is always non-negative. Okay, The bivariate CDF is always non-decreasing. The bivariate PDF is always non-negative. Okay, it should be greater than 0. So the figure 3.5a, b, and c are examples of bivariate PDF for a random variable x. So this just gives us the what you call the bivariate, okay, so to say, PDFs. Okay, these are the bivariate CDF and these are the bivariate PDF, right? So we'll go in detail in much more there, right? So here we have the f of xy, small f x y x x y is always equal to 0, always greater than 0 for the value of x and y both between -infinity to +infinity. And going in the inverse way, if you write the inverse of this,